Okay, so stats one, anytime you read one of these, plan to spend 5 minutes on it. A radio station claims to its advertisers that the mean number of minutes commuters listen to the station is 30. So they claim that their listeners listen to it for 30 minutes. They then surveyed people, and they surveyed 500 of their listeners and asked them to report. So it's just a sample survey. But of those 500, the average number of times listened was 29.11 minutes. So it doesn't seem far away from their claim, which is good news. It was never going to be exactly as their claim, but it does seem close. So then, based on this result, a simulation was run where the mean was 29.11. So when a simulation is run, it's almost always going to be somewhat of a normal curve. And you set up the simulation to run based on a certain population average. And they use 29.11. So it's no surprise that this is peaking around then. Okay. And here is the result of the simulation. So if essentially what this is saying is, if we knew that the population average number of minutes listened was truly 29.11, if we sampled 1,000 times, if we sampled 500 people 1,000 times, our mean would be 29.10, and our standard deviation would be 0.934. So 0.934 above would be 29.934, and 0.934 below, 29 minus 0.934, would be 28.066, which means approximately 68% of the time when you take a sample, the sample will be between, sample will listen between those two numbers, 28.066 and 29.934 minutes. And two standard deviations away, so that would be 95% of the time. So I'm going to go down below 28.066 by another 0.934, would be between 27.132 and, I'm going to go another standard deviation above here. Mind you, I haven't even read the question yet. I'm clearly just trying to wrap my head around what's going on because I feel strongly that that needs to happen. You get as high as 30.868. So here's our 95% confidence interval, so to speak. So as low as 27.132 and as high as 30.868, 95% of the time. So based on the simulation, is the claim that computers listen to the station on average 30 minutes plausible? Well, the claim 30 minutes does fall within the 95% confidence interval. Explain your response, including an interval containing the middle 95% of the data rounded to the nearest hundredth. So I went out to the thousandth. So based on the simulation, we're just pretty much going to take our notes and put them into a better sentence. Based on the simulation, 95% of the time, listeners listen between 27.13 and 30.87 minutes. So, yes, is the claim that commuters listen to the station on average 30 minutes plausible? The claim is within that interval, and therefore plausible. So just about 5 minutes, as I thought. Okay, second to last question. We're just asked to solve the given equation algebraically for all values of x. Now, anytime in Algebra 2, first of all, when we solve things, we check for extraneous. So don't forget that at the very end here. But for the time being, this is just a radical function. Step 1, if you know your flashcard, isolate the radical. Now, isolating the radical can involve dividing by 3. But dividing by 3 is going to create some pretty nasty fractions, so I don't really want to have to do that. I avoid that. If it's going to create a fraction, I avoid it, and I square from here. So isolate the radical and square both sides. You just have to be careful when you square here. 3 squared is 9. Root x squared is just x. When you square here, you FOIL out. If you can do that in your head, great. If not, remember this is technically what I did. 2x minus 5 times 2x minus 5. I got 4x squared minus 10x minus another 10x is where I got my minus 20 plus 25. And then it becomes a quadratic, so I have to get it equal to 0. And then I can play around with factoring. So I'm going to first try 2x and 2x. Okay, with 25 and 1 makes 50 and 2. That's no good. I'm trying to get 29. 5 and 5 makes 10 and 10. That's no good. And there's no other way to make 25. 1 and 25, 5 and 5. So now I'm going to try 4x and x. So 25 and 1 would create 101. That's no good. But I can flip the order of those because one of them is getting multiplied by 4. That one, 4x and 25x, does make 29. I need it to multiply to get positive 25, so it's either a double positive or a double negative multiplication to get positive. And because it's a negative in the middle, I know it's minus. So when I tee it up, I get 2 answers, 25/4 and 1. And you want to check both of those. So if I check 1, 3 times root 1 is 3, minus 2 times 1 is minus 2. Does that equal negative 5? No, so reject it. And then 25/4 I probably want to check on the calculator. So 3 times the square root of 25/4 minus 2 times 25/4 equals negative 5. So that worked. If you're solving something open response, I would almost guarantee that one of them is going to be extraneous. And our last big 6-point question. So it starts off with a graph, which is pretty great because we can just use our calculators, but it doesn't look like they're giving us the equation. So let's kind of figure out what's going on here. Tony is evaluating his retirement savings. He currently has $318, which earns an interest rate of 7% compounded annually. He wants to determine how much he will have in the account in the future, even if he makes no additional contribution. So this is exponential growth. You could treat it as a compounded type question, but your n would just be over 1, so I'm not sure that would make a difference. So the two equations that we are choosing from are final value equals initial value 1 plus or minus r to the t. Or if you're doing compound interest, starting investment 1 plus r over n to the nt. If you do use the compound interest, because this one really kind of is the bank account and the money thing, your n's would just be 1, so it's happening annually. So if you made that a 1 and you made that a 1, they kind of don't do anything. And it really truly is the same equation either way you look at it. Okay? They were very specific. We're not using x's and y's. We're using the amount in the account as a function of time. And that will equal our starting amount, A, which is $318,000. And then 1 plus our 7% is 0.07 to the t power. So the amount as a function of time, so our equation is in terms of t for time. Then they want us to graph this only from 0 to 20, so we will not be putting arrows on the end of this. And to do that, your best way is to probably steal numbers from a table, okay? And it's going to be tough to get them all exact because this is money and there's going to be decimals and cents involved. But basically, we want to make sure we scale it from 0 to 20. So T is already labeled time, 0 to 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So if you can count by ones, which we perfectly can, wonderful. I don't really know what to count by on the amount until I know what year 0 has, which is 318,000, and what year 20 has. So the fact of the matter is my first point isn't going to be till 318,000. So I don't want to start at 0 and do that. I'm going to use a line break and maybe start at 300,000. And then make sure I go up and I count evenly and space evenly to whatever my 20th year total would be. So I can do y equals 318,000, 1 plus 0.07 to the t power, x power. And if I look at my table, I've got year 0, 318, and then year 1 is 340, and year 20 brings me all the way up to, now it says 1.23E6. You have to know that 1.23 E6 means 1.23 times 10 to the 6th, which means I'm moving my decimal place over 6 units. So 1, 2, and then 4 more, so 4 zeros to follow. So that's 1,230,000 after 20 years. So 1,230,000. So if I'm going from 300,000 to that number, maybe I want to count by 100,000. That would be 4, 5, 6, 7, 8, 9, 10. There would be 1,000,000. So 400,000, 500,000, 6, 7, 8, 9, 1,000 is not a thing. It would be 1,000,000. And then you have 1,100,000, 1,200,000, and so on. You don't need to label all of them, but you need to label some of them. So then if I'm just stealing values, I definitely want my starting and ending point to be exact. So 0, 318. This is 300, this is 400. So 318 is going to be right around there. Again, you do have the luxury of ballparking here because there's no way to be exact with 318,000 when you have to scale so big. I could have spaced these out a little bit more. I could have gone every other as 100,000, but that's okay. As long as I'm not really cramming it too low. And then 20 we said was 1 point. The year 20 was, here's 1,200,000, 1,300,000. So 1,230,000 would be about there. Year 10 would be a good one to grab because it's right in the middle. 625,554. So here's 600,000. Here's 700,000. So this is about 625 because that's as accurate as we can get. So I'm just going to grab 2 more points, the 5, which is 446, and probably the 15, which is 877. See you later. There's 877. Now, these kind of look straight, but just because it's exponential growth, you should know that there's a bit of a bend to that. But that's a good sample of space. Now, by the way, if you tried to graph this on your calculator, you're going to see nothing because I'm negative 10 to 10, negative 10 to 10. And the reason for that is because the numbers are way up here in the 318,000. So if you ever tried doing that and you were confused, let your years go from 0 to 20 and your bank account go from 0 to 1.2 million. I'll do 1.3 million. And now I'll see a much better part of my graph. So there it is, and if you tried to just graph that to steal the image of it, you would have trouble if you didn't understand the whole window process. Okay, Tony's goal is to save $1 million, so determine to the nearest year. So his final amount, he wants to be $1 million. His initial amount was at $318,000. We're earning 7%. We're looking for the nearest year. So we're just solving an exponential equation. This will take logs. We have to divide by the 318 first. Now take the log of both sides. So the log of that equals, bring the t out in front of the log of 1.07, and then just divide by log of 1.07. So I'm just going to type that into my calculator. The log of that fraction, careful with your zeros here, divided by the log of 1.07. And that'll give me 16.9 years to the nearest year, 17 years to achieve his goal. Which makes sense, because we know by year 20 he was over 1 million. Explain how the graph of A of t confirms your answer. Because at 15 years, we were under, and I'm just basing this based on the fact that I know we were under $1 million, but by 20 years, we were over. And that works for my graph, because I only plotted 15 and 20. You could more generally say something along the lines of, at a t equals 17, which is here, you can look over and see that that's right around $1 million. If you wanted to exactly look at that table, 17 years, you're almost at $1 million exactly. That's because it actually happened at 16.9. They did say algebraically, though, so you couldn't have just pulled from your table to answer that question, although your table confirms your answer and gives you your graph.